Okay, tech artists, welcome back to another lecture on deep learning. I don't know how this is going to work, but we're going to do our best to hold our things together, do my best to get this lecture out in between nurse visits and doctor visits and blood draws and so forth. But anyway, we are going to be talking about convolution neural networks. And you're probably going, wait a second, we've heard about that before. And I say, yeah, you definitely have. And you've worked with those before. And we're going to be using that for the ASL MNIST. Now, if we look at what we did on Monday, it's a pretty good for a computer algorithm, but the look at accuracy is pretty good. The loss and the value loss are pretty high, and that's an indication that the data has been overfitted. In other words, the jumps in increments in the adjustments in adjusting the values of the individual uh, in the eventual tensors was too large, and then we're missing some kind of information and nuances. And so, what we might want to do is consider, looking at how we as humans look at objects if we're going to classify them. And that should start to be ringing some familiar things. And that is, we covered this in post-processing called Sobel operators. In other words, the edge detection algorithm. The edge detection algorithm, yes, it's the basis of all cell shading, but it's a real simple algorithm that works really well. That compares the contrast of adjacent pixels, and it uses them to identify where the edges are. And ultimately, we're going to use those edges in order to identify the shapes of the object, and we're going to be looking for those shapes in order to recognize certain things. And just as a reminder, there's the Sobel operator is a two-pass filter. It first does it horizontally, and then it does vertically. And it's the sum of those two passes and decides, okay, is this pixel going to be white or is it going to be black? Okay, just as a reminder, if we look at the horizontal pass, here is our Sobel operator. It's a 3 by 3 matrix, and it looks like this crazy thing. And then so we multiply the current pixel against the 0th one, but we analyze all of these other pixels all into it, and then we come up with our convolution. So we're going to multiply our convolution times this value, and then we're going to multiply all of these values against, and we're going to add them up all against each other in order to come up with our convolution value. And then we're going to do the same thing for the vertical pass. And well, this is an error, but this is the vertical pass, and this is the horizontal pass. Yep, it's swap side. Don't look at the this one. It's wrong. Look at this one. This is the right one. And so we have a convolution X and a convolution Y. And then so what we're going to do is we've got a convolution X and convolution Y. We're going to add them together. And if it achieves greater than some kind of threshold, then we're going to say, hey, this is an edge. So we're going to return white. Otherwise, we're going to return black, saying, no, this is not an edge. So we've seen that before. And if you had a chance, a lot of you have actually implemented this algorithm before. And it's not actually too difficult to implement. So what are we doing this to do with AI? Well, convolution neural networks is all about kernels and convolution. So a kernel is a 3 by 3 matrix. And so what we're going to do is we're going to apply that 3 by 3 matrix on an original image. So if we look at this original image, and then we want to get it blurred, so how do we blur it? Well, we apply a convolution matrix against it. If we wanted to get the edging, well, we're going to do a Sobel operation. If we wanted it sharpened, it's a different one. And we wanted brightness and contrast, we had changed those. We'll just come up with a 3 by 3 matrix in order to multiply every single pixel against, and that will create the outcome. And there is the kernel or the convolution matrix for blurring. There it is for edging, and it's a two-step process. So it's got to be done for both vertically and horizontally. And there it is for sharpening. And there it is for brightness and contrast. Okay, so what does that have to do with it? If, okay, the vertical and horizontal matrices look familiar, well, that should be, because then we realize, okay, this is how we can do it to the actual images. And so what we're going to do is apply the images that we have here against a blur kernel. And well, there it is. There's my blur kernel. And so what we're going to do is we're going to line this 3 by 3 matrix up and multiply it against every center. But we can't actually do it there. So we have to do it at the corner one where 0.025 lies over the first white one in the second row. And then we just multiply against, we shift the matrix over, and then we perform the whole matrix operation again. We shift it over and over. Now, mind you, because the blur kernel consumes some space, we can't actually get a 6 by 6 resulting convolved image. We have to actually get something smaller, and in this case, it's a 4 by 4. And so we're going to introduce a concept called stride. Stride is how much do we shift this convolution matrix over. So we already know that we have a 3 by 3 matrix. We would multiply this against this particular 6 by 3 shape. If we had a stride of 1, we're going to move the matrix over 1 for every iteration. And then we end up with 4 values. Okay, if we had 2, then we shifted it 2, we would have the same input matrix, but then we'd only have 2 values coming out of it. And if we did a stride 3, then we'd only end up with 2 values as well. Okay, so the stride is a way of exploring how much we want to open and limit our values by. Okay, so one of the things we could do is pad our images. So we want to put pad with zeros all the way around so that we'll get our convolution matrix. We're not going to be losing any kind of information. So if we have a 6 by 6 image here, what we could do is convert that into a 8 by 8 image and then apply the convolution matrix against the original matrix. And then what we'll end up with that is a 6 by 6 result out of that. And that is exactly what we're going to do here. We're going to get our original 28 by 28 image, and then we're going to apply the 2 kernels in order to get the horizontal and the vertical. Now, we're going to be using the edge detection, the Sobel edge detection, and we're going to do that for every frame. So we're going to end up with 2 values, a horizontal and a vertical, and then that's going to create 2 stacked images. One is horizontal and one is vertical. And then we're going to do that entirely again to each. And so we're going to have a vertical and a horizontal off of that, and a vertical and a horizontal off of that. And then that's going to end up with 2 more stacked images on top of each other. And then once we have these 2 images, then we're going to flatten them. And so we'll just make one big old string of values. And then we're going to put that into our dense neural network, which is the exact same neural network as our last MNIST thing. We're going to have 2 hidden layers that are 512 nodes deep. It seems like 512 is a favorite thing. And we're going to finally output the 24 nodes in a final output prediction. And if we look at it, how we set this up, we're going to have our input, then we're going to pass it into one convolution filter, and then another convolution filter, and this is going to give us the edges. And then we're going to pass it through 2 more convolution filters, which is going to give us our textures. And then we're going to convert that into, we're going to flatten those out. And then we're going to go through 2 dense, invisible layers. And then it's going to finally go to our output. Okay, one of the things that in order to help speed things up, is something called max pooling. And that is breaking our source image up into little baby cells. Like in this case, we have a 4 by 4 cell, and then we break it up into 2 by 2 cells. And then for each one of these 2 by 2 cells, it just takes the maximum value. So here, this little maximum value for this little cell is 256. This is 153. This is 55, and this is 23. And then we create a new cell based on those max values, and that's max pooling. And we also use another thing called dropout. Dropout is a way of actually just dropping out random nodes within our invisible layer. And so what that does is it creates a certain amount of uncertainty and unpredictability in there. And a certain amount of dropout turns out to be a very good thing. And it forces our network to learn a little bit more. And so dropout is another one of our tools that we have in order to fine tune our convolution neural network. And so this is what the final one is going to look like. We're going to start off with our input. We're going to do a convolution to it and do a max pool. We're going to do a convolution to that and then do a dropout. And then we're going to do a max pool again. Then we're going to do one more convolution and do a max pool of that. And then do a dense, and then an output. Okay, don't worry about not knowing how to invent all of these steps along here. Computer scientists and data engineers spent many hours trying to figure out just the right tool. And so your job is to understand that this is the formula that you would use for creating a convolution neural network. And don't worry so much about how it's created. If you really wanted to go take a more advanced course, then they could go into it in gory details. Okay, so what we're going to do is we're going to create a new notebook in our Anaconda, and we're going to call this CNN MNIST. And I'm going to Okay, folks, I'm going to have to go and do a bunch of bopping around because I only have one monitor here. And I'm going to go ahead and go with this, and I'm going to escape this and then move on to this. And so the first thing I'm going to do is make sure that we have our Anaconda Anaconda shell going on here. So I'm going to click on here, click on Anaconda shell, go to the Anaconda power prompt, select that. All right, we're going to go here, and I forgot what it is, so I'm going to make sure it's a conda env list. That'll give me a list of all my environments. And we want the TA20 demo, so we're going to go activate TA20 demo. I forgot to put conda. Conda activate TA20 demo. Now, what you could have done also, because the PowerShells remember what you did last, you could have just hit the upward arrow key and just eventually hit, there it is, kind of activate. Ooh, there's a one that was a different one that I used. And there's all the other stuff. So there it is, kind of activate TA20 demo. Okay, and then we're going to run Jupyter Lab. So I'm going to go up here. Oh, here we got Jupyter/lab. And we're going to execute that. And it's going to pull up. And there we go. Okay, so I'm going to navigate to my project. There we go. So it's TA20 AI demo. I'm going to drop into that. And so there we have our three functions here. And then I'm going to go ahead and look in to see if we can create a brand new project here. So I'm going to click on the plus, click on Python 3, and then I'm going to call this ASL or CNN ASL. So I'm going to right click on here, go to rename, ASL underscore CNN. Okay, so that means the American Sign Language. We're going to create a convolution neural network. All right, so we've got that going to ASL CNN, and then I'm going to go ahead and I'm going to copy the first section off of this. All right, so I'm just going to copy this, and I'm going to explain what all this is. And I'm just going to go ahead and paste that in here. Okay, we're going to load the libraries and set our devices. So we're going to import torch.nn as and torch.nn as nn. We're going to import pandas as pd. We're going to import torch. We're going to import torch.optim and import atom, and then import our torch utility basis. And then I'm going to go ahead and going to get one more. I'm going to set my device, and here it is, a nice one big one statement. in here. There it is, one big old statement here. And then I'm going to print out what my device is, just so I know for sure. And then I'm going to hit Shift Enter to execute this. Oh, okay. Else Torch CPU, Torch CUDA is available. Oh, my stupid name. Okay, there is, I should put a return statement after that. Torch is available. There we go. And that should be fine. Plug, chug, plug, chug, plug, chug. It's gonna go. Okay, there we go. All right. All right, I'm gonna grab the next section that we have up here. I'm gonna grab this, and we're gonna prepare the images. So I'm gonna grab this right here, and then paste that right into the next cell. And so, just like we did for the MNIST ASL, we're going to divide this into our training data frame and our valid data frame. And I'm going to go ahead and execute and load them in. Okay, so we now have our train DF and our valid DF. All right, we're going to come over to the next thing, and then we're going to visualize just the top 5 rows of what this is actually going to look like here. And I'm going to copy these, but we're only going to look at a few at a time here. All right, so, and I'm going to put comments in front of these just so we can make our visualization just a little bit more simple. Okay, so what we're going to do, what this statement does, we're going to sample.df. This is just a sample statement. We're going to grab the top 5 rows. We got the training data. We're going to get the head. And by default, we can control the head. The head is just the starting amount. And by default, that's the 5 lines. And so what we're going to do is we're going to create duplicates or copies of those 5 lines and then pass them on to sample.df. We don't want the real values. We just want the 5 lines. And from that, we're just going to copy the labels. We're going to pop off the labels. So the labels don't get, so it's just going to be data values. So let's take a look at what these data values look like. Okay, so the data values that got popped off are 0, 3, 1, 6, 2, 2, 3, 2, and 4, and 13. Okay, so what we're going to do here is then we're going to put sample x, our x value. This is the actual data. And so we're going to go into our sample df.values, and we're going to take a look at that. And there is all of the values, and there's lots and lots of data. But notice that those values are 2x2 matrices, and they are stored in linear fashion, and they're all from 0 to 255. So we're going to have to eventually change that. But let's take a look at the shape on there to actually really understand what we're dealing with. Okay, so there's 5 values. So that means we've got the five top rows, and there's 784 values. So it's 5 times 784, and that's basically 28 by 28. So they're still linear. Okay, so what we're going to have to do is eventually convert those into 2x2 arrays. So we're going to reorganize the data so that we can apply the convolution to it. All right, let's go ahead and take a look at what we got there. Oh yeah, we're going to reorganize the data so we can apply the convolution. And we know that we want the images to be 28 by 28 because they are 284 by 284. Go ahead and put that over here. There's 784. Sorry, my bad. Okay, so we have the width is 28, the height is 28, and the color channels that we're supporting is a value of 1. All right, then we're going to reshape our sample here. We know what our sample is. Our sample is 5 by 284, so we're going to resample that. and reshape it to be 2 by 2. So here it is, we're doing a reshape here. And I forgot what sample X is. It's a, it's a pandas value. And pandas allows us to reshape this. So we go ahead and then we're going to reshape it by using -1 as the first parameter, and the number of channels, the height, and then the width. Go ahead and execute that. And then we have 5 values, and each of the 5 values is going to be one color channel with this 28 wide, or 28 high by 28 wide. Okay, so we've got that, and so our sample thing more or less works. Okay, and so what we're going to do is create our custom data set. Now, our custom data set is pretty much going to be the exact same custom data set that we created for our last thing. So if we copy that, it really is not going to be different. So we're going to start off by creating a class declaration. Say my data set is of type data set. And then what we're going to do is we're going to create our base data frame, and we're going to copy that over into XF. And then Y is going to be the label values. All right, so let's take a look at that. Okay, so here we're going to pop the label, and here we are converting the values from 0 to 255. We divide it, be normalizing them between 0 and 1. Here we're going to be reshaping them in order to form the two-dimensional matrix. And here's where we're turning the images, the two-dimensional images, into two-dimensional tensors. And here they are getting turned into one-dimensional labels. And here's our get item override and then our length override. Indentation blocking. Okay, from line 4. I don't remember where line 4 is, so I'm going to go over here and go to view, and then we go show line numbers. Okay, line 4. XDF, unexpected indentation on line 3. So, oh, look at that. Okay, so all of these need to be inset. Oh, okay. So let's go ahead and re-execute this cell. Inconsistent use of tabs and spaces. I. Okay, so what we have to do is hit the backspace here, and then hit tab. And now we have to do the same thing here. Backspace, tab. Backspace, tab. Backspace, tab. Backspace, tab, and then backspace, tab. Shift enter. Inconsistent use of tabs and spaces in indentation. Let's go ahead and I'm going to backspace this again all the way. Okay, here, and I'm going to go and enter this again. And now let's see if this works. Inconsistent use of tabs and spaces. Okay, so that means that this one is not correct. So let's go here, here, okay, and then boom. Okay, and then class data set. So let's try this again. Okay. Okay, so that worked. So I'm going to have to go and backspace this again. And then backspace there. And does this work? Okay, the length is going to be the same. I'm going to backspace it. So we get to here, all the way here, and then I'm going to enter, enter, and hopefully that should do the job. Inconsistent self on line 12. Line 13. Okay, so we're going to have to do this over and over again. Just backspace it around, and then we're going to have to do this here. Backspace here. And then we're going to try to do the same thing in return. Okay, enter, and that did it all. Okay, that was annoying, but one of the problems of using Python uh, with PowerPoint. Oh well, c'est la guerre. All right, we've got our data set created. Whoops, and there we go. So let's go ahead and convert our data to data sets and then to data loaders. That will work here. I'm going to grab all of these. Come on over here into the next cell, and then Control V to paste. Okay, so the batch size is 32. That means I want this done in sets of 32. All right, so the trained data is my data set is trained DF. So here's our data set, and then we're going to use that in order to convert that into a data loader. And then we want the train end to be the size. I'm just going to do that so that valid data. We're going to create a valid data set, and then a valid loader, and then the size of the valid set. There we go. All right. All right, folks, not an emergency, just some news. So what we're going to do is visualize the train loader. So I'm going to go ahead and capture this next section, toss it in here in the next cell. Now I say batch equals next iter train loader. So we're going to look at the first 32 elements of the train loader. I'm going to go and enter. And well, there they all are. Okay, and notice that there are 32 values, and there we're first do the 8th value, the 17th value, and 11th, so forth. And if we run this again, we should get the next batch. We see that the numbers change, and that's because it's going by the batches. It's just iterating through these train loaders, next, and so. All right, so that is working the way we want it to. Very good. Now what we're going to do is we are going to create our convolution model. And I'm going to grab the first part here. I'm going to do this in 2 sections. All right, so we know that the number of results that we're going to get out of this is 26. So the number of classes we have here is 26. And our kernel size is 3. Actually, what it means is be 3 by 3. And then we know our flattened image is going to be 75 by 3 by 3. So 75 values times 3 times 3, which is, oh, I don't have my math here, but it's 75 times 6, and that's what one flattened object is going to be looking like. And that's going to be our input going into our more traditional neural part of the network. And I'm going to come over here and grab this. And now here is our entire CNN model. Okay, there's a lot to do here, so that's why I copied this. So here's our first, we're going to declare our model as a sequential, and here's our first convolution. And then we're going to say here, okay, we want here batch norm equal that, and then we're going to batch norm, and then we're going to do a ReLU, and then we're going to do a max pool. And remember, the max pool goes 2 by 2s, and it does a stride by 2, and it takes 2 by 2. And so what it's going to convert, if you have the 28 by 28 versions of these, it's going to convert them to 14 by 14. And then we're going to do our second convolution. We're going to do our conv2d and convert it to 25 by 50. Here's our kernel sizes, 3 by 3. We want a stride of 1, padding of 1, and that's going to convert each of these layers to 50 by 14 by 14. Batch norm 2D that is going to normalize them into units of 50. Then we're turn them into rectilinear units. I'm going to drop out of 0.2, and the max pool is 2 on a stride of 2. And then we're going to do a final third convolution, which is basically the exact same steps, but notice here that the max pool stays constant, and the match normal 2D kind of changes. It goes from 50 to 25. And then we're going to flatten them. That means convert them into one-dimensional. And then we're going to fit all those images into 512 nodes. Then we're going to have a dropout of 0.3. We're going to send them to reloos, and then send them over to another linear set of 512 with the number of n classes as the number of outputs. Now remember, we're not expected to know exactly the exact sequence on all of these. What we are supposed to know is what each of these functions does and how it can be manipulated to change these parameters. I didn't invent this, and you're not expected to invent these at this moment in time. So let's see where our problems are, if there are any. Okay, so it accepted it. We are doing good. All right, so I'm going to come over here. We're going to look at we've got that. And so what we're going to do is we're going to compile the model, and we're going to set its optimizer. All right, so come back over here. We're going to compile the model and set its loss function and set its optimizer, and then we're going to print out what the model looks like at the end here. Make sure that that's lowercase because it's set as a lowercase right here. I'm going to hit enter. Oh, there it is. It printed it out, and there's all 17 layers that we go into the CNN convolution neural network, our ASL network. All right, now what we have to do is define our testing function and our validation function. Now these are going to be the exact same that we used for our MNIST ASL, so they're not going to be too surprising. Oh, before we do that, we're going to use the get batch accuracy. We're going to copy that and then paste that right in here. Okay, that's going to be the exact same. Hit enter. All right, that's going to work. Now here is our validation function. Once again, this is the exact same validation function that we used before, so we're not going to go into too much detail on describing its detail. That you'll have to go back to the last lecture in order to get its gory details. Okay, we're going to look at that. Okay, so that's good. And then we're going to get our training function. So we've got our validation and our training function. Paste that right in here. Enter. Oh, we got an indentation, line 6. Okay, so, that is an indentation error. Okay, so if we hit this, hit there, let's see how good that is again. I'm going to go ahead and hit Shift Enter. And unindent does not match any outer indentation levels. Okay, so this is Python being wacky. Okay, now try it. Model train. Unindent does not match any outer indentation levels. Okay, so what is the deal here, gang? Train loss. Okay, we're going to have to go ahead and set all these and make sure that they're done exactly right. And then let's try this. Yep, and so we're going to have to do it for every line here. I don't know why it does this for some and not for others. I don't know. You set this to be as optimized as possible, but you're always going to end up screwing up someplace. And so all I'm doing here, folks, is just going back and then resetting my indentations. to make sure that they are exactly the same. And then here's our accuracy. And then we are going to print out the final value. Okay, there we go. And now let's go ahead and shift enter. There we go. And we've got our validation function and our training function. So the only thing left to do now is to execute our script. Okay, there we go. Number of epochs, we wanted to go 20, so it's going to be a little bit more. And we're going to go to epochs in the range, and we're going to print out the epoch number. We're going to do a training set and then a validation set. Let's go ahead and get this going. And if this all goes well, then we'll get some values for our epoch, or else we're going to have to deal with more errors. Let's see what we end up with. Keep your enthusiasm up, folks. Keep it hopeful. Isn't there yet? It's taking its good old time. Hang in there. We should be getting some value soon. Hurry up. Boy, I want to try to start figuring out how to take advantage of my GPU. This is taking forever. This is like too long. I wonder why my computer is running so slowly. It has to do with the heat. Not quite sure. Oh, wait a second. I forgot to scroll down. Oh, there it goes. Oh, so look at this. Already it's got the training thing. It's got like, oh, it got a point 90%, which is better than the 70% that we ended up with our MNIST ALL. And our validation started off at a very high 95%, almost 96%. That's way cool. So what I'm going to do here is just leave this as is for now. And I'm going to let this percolate and calculate. And I'm going to come back to you when it's finished. Okay, gang, we've finished off and we've finished the calculation and training of our model. And if we look here, we finish off with a train loss, and we only lost 3 out of what, I don't know how many thousand it was, but that's at 0.9992%, so that's almost 100%. Now the validation, this is the one this is the one that matters. Okay, so we missed about 27 out of the whole training set, which means it's about 97% accurate, which is actually pretty good. If we take a look at our MNIST ASL, we realize that our accuracy was only about 80% when we have in there. So that definitely identifies that, okay, that is definitely a better job. Now, if we look through the actual build history, we realize that it does get a little bit higher at some spots. And so it hovers right around 97. It almost gets to 98 here. But then as we continue through the epochs and so forth, we go into areas and it relieves, put in a little bit of instability. But 97% is pretty good. But honestly, folks, we can do even better. Okay, train in for the lecture next week when we go into how to add randomness and augmentation into our CNN neural networks. All right, until next time, have a great weekend, and I'll see you next trip.